pi-electron systems, preparation and characterization of organic main group, inorganic reactive intermediates, and many, many more. So with this, a brief introduction, it's my, again, great honor to invite Professor Josef Michl to begin his tutorial. Thank you very much.
Thank you for the very kind introduction. Let me start by asking whether I can be heard well.
Yeah. Yes. Yes.
The sound
yes.
good? Can you hear and understand?
Yes. Yes, Professor. Yes. Yes.
Okay. Excellent. Well, you have asked for a couple of lectures, tutorial lectures on singlet fission, and it probably is appropriate to first say a few words about the history of singlet fission. You can read more about it on this in the articles mentioned on this first slide, which has my two affiliations, one at the University of Colorado in Boulder and the other at the Institute of Organic Chemistry and Biochemistry of the Czech Academy of Sciences in Prague, in the Czech Republic. The first review that's mentioned here, entitled Singlet Fission, appeared in 2010, and it is a summary of pretty much everything that was known about singlet fission at that time. Singlet fission, in a way, is an inverse of triplet annihilation. It is a process in which one excited singlet state produces two triplet states, and it was observed accidentally, unexpectedly, in Canada, actually, in the mid-60s. And it was studied together with triplet annihilation by a group of people who figured out what is going on, and within a few years developed a fundamental picture of how the phenomenon is to be viewed and understood. And thereafter, interest in singlet fission more or less died off. There were very few papers that followed, and the process acquired a reputation of an obscure and not very efficient phenomenon. Until in the beginning of this millennium, Art Nozick at NREL, the National Laboratory for Solar Energy, very close to Boulder here in Colorado, proposed that it might be actually useful for increasing the efficiency of solar cells. And it was in 2010, actually, that several papers, 3 papers, appeared showing that it does not need to be an inefficient phenomenon, that it can be actually very efficient. And so interest in this started to grow. The next review article that is listed here is only 3 years younger, and there others followed. I only give one more here as a reference. I also give a couple of references to introductory texts in which the phenomenon is explained to beginning students and to general scientific audience, people who do not have any particular knowledge of photophysics or photochemistry. Maybe I should tell you as a half joke, but it's actually true, it's not an invented joke, how I became interested in singlet fission. I was an organizer of a workshop on various aspects of photophysics around the first year of this millennium. And it was organized in Quilmes, Argentina, in the Andean mountains. We collected mostly students and some professors in a small hotel at an archaeological site called Quilmes. And it was 5 hours by bus from the nearest airport and something like 3 hours for the nearest town. And that allowed us to keep the students on the spot. They had no other place to go. So they had to listen to lectures. And once I had dinner there, sitting next to Art Nose, the person, and he asked what I was working on. So I told him about all kinds of beautiful experiments in physical organic chemistry. And he's very polite. And after about 20 minutes, he asked me, well, Joseph, this is very nice, but why don't you work on something useful? I was a little taken aback, looked at him and said, well, what do you mean? I mean, what would be useful? He said, well, why don't you work on solar energy? That's really going to be important for mankind. And so I asked him, well, okay, what about solar energy needs to be solved? And he told me about singlet fission. He said, you know, I'm a physical chemist. I cannot synthesize the compounds that are needed and investigate them. I only can work with what I can purchase. But you are an organic chemist. You should be able to do it. Well, so I became interested and I started to work on singlet fission. So that's how I got involved in this phenomenon. So let me first say, indicate on a few slides why I think, and certainly Art Nozick thinks, that singlet fission is important. We all know about the problems associated with burning fossil fuels, production of carbon dioxide, and the increase of its concentration in the atmosphere, and its function as a greenhouse gas. That is something that has been known already to Svante Arrhenius in the beginning of the 20th century. It's nothing new. In his time, people were not burning so much fossil fuel, and so it did not matter. But gradually, it has become clear that if we continue doing that, it will have some very severe consequences. The explanation for the greenhouse gas effect that's usually given, it's somewhat oversimplified. People often say that the atmosphere transmits UV visible radiation that comes from the sun and heats the surface of the earth, but it absorbs the infrared radiation that's emitted by the warm earth, and most of it is the water in the atmosphere, but the CO2 makes a significant contribution also. Actually, without such absorption, the earth would be quite a bit cooler than it is now. And the objection to that explanation is that, well, there is already enough CO2 in the atmosphere that if you put in some more, it won't matter, because already most of the IR radiation in the spectral region where CO2 would absorb is already absorbed. So a more detailed explanation actually exists that is called positive radiation forcing. I will not go through that in detail. It just explains that, yes, in spite of this observation about all the IR already being absorbed, it does make a difference if we add more CO2 into the atmosphere, because that IR radiation will be absorbed sooner. As it leaves the surface of the Earth, it will not go as high in the stratosphere as it otherwise would. And so the edge of the atmosphere that determines the overall radiation loss, radiative loss to the rest of the universe is going to be cooler, and there will be less radiation, more heat will be conserved at the surface of the Earth. So this indeed is a problem, the CO2 as a greenhouse gas, and this is nowadays generally acknowledged, except by a few politicians. there's a lot of evidence for the warming. I have photographs here of one of the mountains that I had the good luck of climbing when it still looked like this. This is the Kilimanjaro in Africa. Now, in the year 2000, most of the ice is gone. Here you see the Arctic ice, how it changed in 30 years, most of it disappearing. And there are many other pieces of evidence for the warming. Here, for instance, is a list of temperature anomalies. The average temperature in these years, the 30 years between 51 and 80, is indicated by this white stripe in the middle. That's where the zero sits. But already then, of course, there would be events where the temperature, the average temperature, at averaged over a large number of stations all over the world, would be higher, and that's shown in red, or lower, that's shown in blue. Well, if you now take this curve and repeat it in the following decades, this is 81 to 91, 91 to 2001, and so on, that's this dashed line. And you can see how the actual temperature events shift to higher and higher temperatures as time goes on. Now, in this region, previously there was just absolutely nothing. Now we have something like 10% of incidence. So there is just no doubt nowadays that this is a serious thing. This slide shows a publication that's almost 10 years old now, which indicates the effects of what the humans could do to reduce this CO2-induced warming. If we start in a particular year, say this year or last year, 2020, or 20 years from now, or 40 years from now, if we at that time start reducing the emissions that we now put into the atmosphere, and we could reduce them by 2%, 4%, 6%, and so on. These lines indicate what will happen in time. So if we right now reduce the emissions by 8%, the total increase that we will is going to be about 3 degrees Fahrenheit. If we wait and start with the reduction later, the increase will be bigger. And if we do nothing, it will be tremendously big. So we need to work on this. And I'm glad that starting on January 20th, the United States will join the Paris Agreement again and work with all other nations in the world to try to reduce these emissions. The increased temperatures have some severe consequences. We're already seeing some of them: warming and unusual weather, hurricanes. There is increased disappearance of the polar ice caps, sea level rises, both because get warmer, so the volume expands, and the ice, and also because the glaciers that now store a lot of
Professor Michl. Professor Michl.
in the form of ice are disappearing, making these more.
Hello, Professor Michl. Your voice is breaking in between.
Yeah, we are losing connection.
Yeah.
Can you?
Can't hear you clearly.
We can stop the video from his side, actually, Satish. We can tell him to stop the video.
I did. Oh, we lost him.
We lost him.
Yeah.
You can hear me perhaps again?
Yes. So now we can hear you back again. Maybe you can stop sharing your video. The audio is going to be sufficient because I guess there is some connection issue.
Well, that will not be very easy because I'll be showing spectra and things like that, and that's not so easy to explain in words.
No. We are sharing the slides. That's okay. You can continue sharing the slides. I just wanted your video to be switched off. Just the video of your visual of your house and you. That would be good. But please share your slides again.
Yeah, please.
So how far could you hear me? How far back should I go?
It's that the last slide was on the after the CO2 emissions problem. I guess it was. Do you remember the slide?
Number three and number 4 slide. Please share it. We can identify the slide. Please share your presentation again.
Did you see this?
We are not seeing any slides.
We are not seeing any PowerPoint
right now. You have unshared the slide, so maybe reshare it. It's all fine. We have time. We don't have to worry about that.
Well, let me see whether you will share now.
Yes, it's being now. Yes. Okay. Now, if you go forward with your slides. Let's go forward. Yeah, we covered this. No problem.
One more.
We covered this.
Yeah. Yes.
We were here. You were covering. Yeah. So this did not. This will now come. Okay. So.
Okay, that's fine.
Yeah.
The one before just had a list of the bad things that happen with the global warming, and we don't.
You can start from here. You can start from here. Yeah.
Very good.
Okay.
So if we decide that we want to use some renewable energy source, we have many choices. One can think of wind energy and tides and ocean currents, geothermal, hydroelectric, biomass. And I show here the estimates of how many terawatts are extractable from these various sources. And they are all important sources. But if you compare the 2 to 4 or 2 to 12 terawatts with what the solar energy is, that's 120,000 terawatts. There's just no comparison. There is so much more energy. Of course, most of this cannot be captured, but it is estimated that something like 600 terawatts of solar energy could be practically captured. Well, that is 2 orders of magnitude more than we can get from these other sources. So it would be fairly logical to say, let's take a good look at how much we can do with solar energy. I show here the expected shortages that would have to be replaced either with renewable or non-renewable sources. And you see they are in the tens of terawatts. So there's plenty of solar energy to take care of these expected deficits if we can do it in a way that is economical. So how do solar cells actually work? Perhaps all of you already know that, so let me just briefly summarize what happens. The simplest and most common silicon solar cells use a p-type doped and n-type doped silicon, and at their silicon has a band gap of about 1.25 electron volts, and that would be the distance from the highest occupied level, occupied by electrons, to the lowest unoccupied level, and this would be then the size of the band gap. Oh, if the sun were a laser and just emitted at one wavelength, which is exactly equal to band gap, then we would not be wasting energy when we absorb that solar radiation. You would just be taking the electrons from the highest occupied level to the lowest unoccupied level, and there would be no loss associated with that. Then the electrons and the holes would be separated. The electrons would go this way and ultimately to a wire, and the holes, the positive charges, would go this way and ultimately to a wire. And the energy difference between this level and that level would represent the usable photovoltage that we would get from the cell. But of course, in reality, the sun is not a monochromatic source of light. It has all kinds of wavelengths in it. So there will be some photons that have just the right energy, but there will be other photons that don't have enough energy. They just won't get absorbed at all. They are not sufficient to go from here to here. And so they will be wasted. They will not be absorbed. And then there are other photons that have more energy than is necessary. And so, for example, a hole can be excited from here to there. But very rapidly, the electron will relax from this higher level down to the band edge, and the hole will also relax to the top of the occupied band gap. And we will not get any more energy from that photon than the band gap. And so this excess from here to here and from here to here will be lost. Well, if you combine these two losses and use your knowledge of the distribution of solar photons, you'll discover that the best you can do is only about 1/3 efficiency. That's known as the Shockley-Queisser limit. And it's a paper that appeared in the early 60s. I discussed it once with Professor Queisser, and he told me that they had a very hard time getting it published. The journal editor said, well, this is all correct, but it's totally uninteresting. Nobody cares. Well, in those days, perhaps very few people cared, but nowadays, it's one of the most cited articles ever in that journal. So this is how the conventional PV cell works. There are other types of cells, but they operate on a very similar principle. Now, how does it look in practice? Well, in practice, you have several layers that you have to prepare to generate a solar cell. Here's a back contact that's where the wire is attached on one end, and then you have N-type semiconductor and P-type semiconductor. Those are the two layers I told you about. Then you have an anti-reflection coating, some adhesive, but let's be transparent, and a protective cover, usually glass. And this is what the cell looks like in practice. And it can be produced relatively cheaply because the number of layers that are involved is not very large. Now, what will the solar cell do? Well, let's talk about that. What I show here is a graph that was published by Shockley and Queisser, and they showed how the efficiency of the cell that they were using, the combination of two doped semiconductors, depends on the size of the band gap. Well, you can vary the size of the band gap by choosing different materials. You don't have to use silicon. You can use many others, and each one will have a different band gap. And it turns out that the band gap should not be too small, and it should not be too big. Either way, you go away from this maximum, which is at about 1/3. The maximum occurs just in the region where silicon has its band gap. That's one of the reasons why silicon is so good for these solar cells. Let me just repeat why it is that the efficiency drops if the band gap is too small, and it also drops when it is too big. Well, it's easy to understand why the efficiency drops when the gap becomes too big, because then the amount of photons that don't get absorbed at all increases, and those and their energy are wasted. The reason why it drops also if the band gap is too small is that now you are increasing those losses that I described before, when the photons have unnecessarily too much energy and you're only taking as much as corresponds to the band gap. Well, if you make the band gap very small, you're taking out very little energy. So this curve is dictated by the properties of the solar radiation. This is what the solar radiation distribution looks like. It's there are several curves here. What I show with the solid line is the theoretical blank body spectrum from a body whose surface has the temperature that we find at the surface of the sun. And you can see that the observed radiation above the atmosphere, that's this yellow area, fits very nicely with that curve. The amount of radiation that makes it all the way to the sea level is smaller, because the atmosphere will absorb some of it. And you can see how the absorptions by water molecules here at this wavelength and this wavelength and so on reduce the amount of radiation that makes it to the surface. And you can also see that in this region, you get a total loss of the radiation. Well, that's because you will have ozone absorbing there. And that's just as well, because that protects us from these otherwise harmful sun rays. So if we use a silicon with its band gap that's located somewhere around here, about 1250 nanometers, that means that all of the photons in this tail are lost. They just don't get absorbed. And the photons that are at that particular wavelength are used efficiently. But the ones that have more energy are at shorter wavelengths, lose much of their energy, and only the amount that corresponds to the band gap is actually utilized. So if you are at half the wavelength of the band gap, somewhere here, you're losing fully half of the photon energy. You're just heating the solar cell. So this is an illustration of the problem I just described. Now you can do something about it, and what you can do is the following. Instead of having just one material with a particular band gap, say here, you could have several of them put on top of each other. So then you would have one material that absorbs the high energy photons and produces a high voltage, and then those photons that pass would go and hit another interface that produces a lower voltage, and another one that produces a lower voltage, and people have actually constructed such cells. So here is an example. This is a cell of the kind that uses several materials. You know, we start here with gallium indium phosphide, which has this band gap, and then you have another band gap and another band gap. But you have to meet a condition. The current that flows through has to be the same across all these interfaces. And so constructing a cell like this is immensely expensive. It's all right if you need a solar cell for a satellite, because the cost there is negligible relative to the remainder of the satellite and the rocket and so on. But this is not a way to put solar cells on everybody's roof and supply the world with electricity. It's just prohibitive, by orders of magnitude, prohibitive. So this will not work. What else can be done? And this is where singlet fission comes into play. The way that singlet fission could help with the problem is as follows. In singlet fission, you need at least two chromophores, two molecules. They could be the same chromophore, both could be pentacene, for example. And I show two processes here. Schematically, in this energy diagram, energy is plotted vertically, and this is one molecule and this is another molecule. They are in contact with each other, they communicate. The first step is an ordinary absorption of a photon. Well, we don't need to talk about that much. It just produces an excited state, say in molecule number 1. And then the actual process of singlet fission is what is called here number 2. That's a process in which that excited singlet molecule takes half of its energy, excitation energy, and donates it to the other molecule. So it itself comes down from the S1 state to the T1 state, whereas the acceptor molecule goes from its S0 state to its T1 state. So you end up with two triplets where you started with one singlet. This is indicated in somewhat more detail. The excited singlet reacts, so to say, with a ground state singlet, and it produces a pair of triplets next to each other. And these two triplets are coupled into an overall singlet. One of the triplets, for example, would have 2 electrons with spin alpha, and the other one would have 2 electrons with spin beta. So altogether, you have no net spin angular momentum, and you have a singlet state. And that is good, because you're going from a singlet excited state to a singlet excited state. There is no spin forbiddenness here. This can be an extremely fast process. And indeed, in some molecules, in some solids, it's known to proceed faster than in a time of 100 femtoseconds. So this can be a very fast process. It is spin allowed. Now this is so-called bi-exciton, which is composed of these two triplet states. Can you still hear me?
Can hear you, yes.
Yes, yes.
Okay, good, thank you. That goes through a relatively complicated development that we'll talk about later, until the two triplets separate and diffuse freely through the solid, and they go to an interface where the charges separate, and you can then collect the charges, and they contribute to the output of the solar cell. Now notice that if we want this process to be fast and competitive with all other decay modes of that excited singlet state, it has to be either isoergic or maybe slightly exoergic. It cannot be endoergic. If it were endoergic, it would be slow. You would have to wait for thermal energy to help to get to the bi-exciton product. What that means is that the triplet level has to be halfway between the ground state level and the excited singlet level, because then this amount that's available will be equal to the amount that's needed. In that case, you can have a triplet yield up to 200%. Here is the statement expressed mathematically. And of course, you can start wondering what will happen to the triplets. Yes, they could diffuse apart and be useful, but they could also annihilate. Triplet-triplet annihilation is a known process. And if that happens, you could go back to an excited singlet, or you could go to another excited state, and you would be back where you started. That would not be very useful. So it is usually good if this is a process that's slightly exoergic, because then it will not be going back to where it came from so rapidly.
Can I ask a question, Professor Michl?
Yes.
Yeah, so you mentioned triplet annihilation. Can I just sort of distinguish it from a TT, the TT1 relaxation? So that photophysics of TT1 relaxation, 1 TT, that means a singlet TT relaxation, will it be similar to, say, for example, annihilation?
Well, the biexciton state, which I think is what you're talking about.
Yes, the
right?
biexciton relaxation. Yes.
The biexciton state can indeed decay in other ways than
Yes.
just the
Yes.
two triplets diffusing apart.
Right.
And sometimes that is a big problem.
Yes.
I will talk about a dozen ways in which the process that's outlined here can go wrong.
Okay.
You can go astray in each one of these steps.
Sure.
And some others.
Okay. Thank you.
I'll talk about that later. Yes. Let's see how what the consequences would be if we had a material that performed singlet fission efficiently. You could say, maybe I should go back to the slide here. You could say, fine, you have made twice as many excited states. So if everything goes well, you'll have twice as many holes and twice as many electrons that you collect on your electrodes. But the voltage will be only half of what it was before, because each of these triplets has only half the excitation energy of the original singlet. But since the efficiency or the output of that solar cell is the product of the voltage and the current, you have not gained anything. And this is an issue that needs to be addressed. Is it really true? Will you gain something? I have here a picture that shows how it would work. You would again use, say, a material that has a band gap over here. These photons would still be lost. They are not absorbed. The photons that are twice as energetic as this, instead of 1200, there would be 600, would be absorbed by the singlet fission capable material. And so they would be producing two pairs, whole electron pairs. And the losses would still be there because not that many of them will have exactly this energy. Many of them will be shorter wavelength, and the difference again will be lost, but the losses would not be nearly as big. You'll only be losing the distance from here to here, instead of losing the whole distance from here all the way to there. But what you clearly need is another layer which would absorb those photons that are not absorbed by the singlet fission active material. And they would be absorbed by an ordinary material that produces only one electron hole pair. And again, there would be some losses because you would have to lose the distance between here and the place where the photon wavelength lies. But overall, clearly, you would have smaller losses. And how it would be done in practice, you would have, this is for an example that's a little different from the silicon cell. This is known as the dye-sensitized cell. This would be a cell developed by Grätzel in Switzerland, or what's now 30 years ago almost. He uses a paste of nanocrystalline titanium dioxide particles in acetonitrile, and they are saturated, their surface is saturated with a dye. The dye absorbs visible light, whereas titanium dioxide, that's shown on the diagram here on the left.
Professor
This
Michl.
is the top
Professor Michl.
of the valence band of TiO2. Yes?
Yeah, there are two questions from panelists. Yes. I will let the panelists ask the question. The first question by Professor Sudipto Maiti. Sudipto, could you unmute yourself?
Yeah, hi, Professor Michl. This is Sudipta Maiti, and I wanted to know if the coupled energy transfer that will go on would generally follow the Forster-Dexter mechanism that energy transfers we typically treat with.
Yeah, the nature, the detailed mechanism of the singlet fission process in which energy is transferred from one molecule to another is something that we'll discuss next time. It is relatively complicated. There are two mechanisms that contribute, and one of them is sort of analogous to the Dexter mechanism, and the other one is actually going through virtual charge transfer states. But I will get into that in more detail in the next lecture.
Thank you.
What was the other question?
And the other question is by Professor Ayan Datta. Ayan, could you unmute yourself and ask the question?
I mean, maybe I can wait till the end of his lecture. The idea was like, if you have an excited kind of couple triplet state, I mean, its propensity to go back to the initial singlet excited state with respect to relaxation to a kind of a bi-exciton state. I mean, so the internal reorganizations, I mean, the vibronic coupling, I mean, the human drive factors also are important, right? And what time scale it would be interesting to look at it. I mean, if you would like to comment on it.
Yes. A little later today, actually, I will get to the use of the Fermi-Golden rule for describing the rate of singlet fission, and there we'll see the density of states term, which is what you're asking about. And so if you bear with me for just a few minutes, we'll get to your question.
Thank you. Thank you, Professor Michl. Yeah, please continue.
Sure. So I'm just explaining here for those who may not be familiar with the Grätzel cell, how it works. You could make a cell from titanium dioxide itself, but the band gap is huge. It's about 3 electron volts. So most of the photons, including all of the visible photons, would be lost. They would just not be absorbed. So the attachment of a dye to the surface of these nanoparticles, which is huge because the particles are really small, as shown here, 100, maybe 10 nanometers to 30 nanometers. That dye absorbs at much longer wavelengths, so it absorbs the visible light. Here is the level for the dye, and this is the excited dye. And the excited dye injects an electron into the conduction band of TiO2. The electron jumps from one of these particles to another until it makes it to the electrode. And that, of course, leaves a positively charged dye. The dye has just lost an electron. But in that acetonitrile solution, you have a electron donor, iodide. And the iodide can donate its electron to the dye and restore its original neutral state. And the iodine atom, which is generated this way, will dimerize to give you I2, and the I2 will add another iodide to give I3 minus, and the I3 minus can diffuse to the opposite electrode and take an electron from that. You get iodide back, and you have now separated the charges. And this is how the cell operates. So if you wanted to make a Singlet fission dye-sensitized cell, you would just have to have 2 layers here instead of just 1. There would be a layer that absorbs, say, with a band gap of 1.1 electron volts, and above it, before the light gets to it, it would have to go through another layer, which would have the singlet fission capable material, and it would absorb with a band gap twice as big, 2.2 electron volts. Well, that layer would be producing 2 pairs, electron hole pairs, that would be at 1.1 volt excitation energy. And the second layer, the one that people normally use, would just produce one such pair. But all of these holes and electrons would be the same. You don't need any matching of current. So that makes it a cheap cell. And you would go and separate charges. And now you can ask, well, what will the efficiency curve look like in this case? This is an energy diagram that shows what I just described in words. You first go through a layer of material that absorbs at 2.2 volts, and that has the singlet fission capability. It makes two triplets. Each triplet can inject an electron, and then the light goes, the remaining light goes into the ordinary layer that produces only one such pair that also makes it to the conduction band, and it's replenished from that relay, the iodide. And this scheme would now produce the red curve. Before we had the blue curve. And you can see that the red curve has a maximum at an energy of band gap energy, which is not terribly different, maybe a little bit smaller than the blue curve. But it is quite a bit higher. It's not quite at 1/2, but it's almost at 1/2, something like 47%. That would be an increase from the 1/3 to 1/2 that may not look big to you, but actually that would be a huge step forward. Nowadays, when people work with cells such as these, there will be a team of many people working for a year or two, and they manage to increase the efficiency by 1%. And that's a big success. So now if you're talking about increasing it by something like 15%, that would be fantastic. So this sounds good as a matter of principle. This actually was outlined by Nozick and his collaborator Hanna early in this millennium. Now, does singlet fission actually, how do we know that singlet fission actually occurs? Here is an experiment that shows that. It is an experiment on a material that, it's an experiment from our laboratory in collaboration with Justin Johnson and Art Nozick at NREL. We came up with this structure because we thought it might have a good chance to do singlet fission. And it turned out that we were right. With a large amount of luck and a little bit of intelligence, we predicted a good compound. And this was the paper in 2010 that I mentioned was one of the 3 that suddenly showed, yes, you can do this efficiently. 2 different measurements of the triplet yield were done, and at 77K, it was with the experimental error of 200%, which is the theoretical maximum. It's a little less at room temperature and also a little less at lower temperatures like 10K or 20K. Now, what is shown in these pictures? This indicates measurements of transient absorption. One deposits a layer, thin layer of this material, it's called diphenylisobenzofurane, on a transparent substrate and measures spectra through that combination of layers, the organic layer on quartz or sapphire or glass or something like that. And one measures the absorption of the sample after a short pulse. The short exciting pulse typically maybe 100 or 200 femtoseconds long, excites some fraction of the molecules into the excited state. We ordinarily don't want too many of them to be excited into the S1 state, because then we could have S1 annihilation, and that would complicate everything. So the intensities of these pulses are typically in nanojoules. They are quite weak pulses. The fraction of molecules that are excited into that excited state is relatively small. The excited state has a different absorption spectrum than the ground state. And that spectrum differs, as you can see, in optical density by a small amount. This is multiplied by 1,000, so this would be 1/100th. And but one can measure it fairly accurately, and one can measure at different wavelengths, and at different wavelengths one can observe different species. For example, the triplet that we see is forming increases as one goes from time 0, as you can see on the red line, and reaches a plateau and then remains basically constant indefinitely, because this is on a scale from 0 to 200 picoseconds. And the triplet in a solid of this kind will live for many microseconds, maybe even half a millisecond or something like that. And so on this scale, it's basically living forever. So it reaches a plateau and stops. And you can also follow what happens in the excited singlet state, and you can look at the depletion of the ground state and so on and so forth. The one picture that I want to point out is this inset here. What that shows is the bleach of the ground state. As the initial pulse, this also goes from 0 to 200 picoseconds. As the initial pulse goes through the material, you can see a drop in the absorbance that's due to the ground state. Well, that's logical. The pulse excites molecules from the ground state, so there'll be fewer of them in the ground state, and you see this drop. If we call the magnitude of that drop -1, we have just accounted for the initial excitation of a certain number of molecules to the S1 state. But if we continue to look at the number of molecules that are in the ground state in time, we can see it continues to drop. It continues to drop, and it almost drops to -2. So the initial loss is just about the same as the slow subsequent loss. Why does it continue to drop? Well, it continues to drop because of singlet fission. Those excited molecules in S1 state will react with molecules in the S0 state and remove them from the ground state. So the amount of the ground state continues to drop. And it drops with a certain time constant. It corresponds to about 25 picoseconds. Now that's the rate at which the singlet fission is taking place, or the inverse of the rate. This is the time. And so this way you can measure how close you come to -2, and from that you deduce this result, 185 plus minus 30% of triplets formed with this time constant. So you can sort of watch the singlet fission process occur in front of your eyes. You can see the ground state gradually disappearing as the S1 molecules transfer the energy to S0 molecules, remove them from the ground state, and produce the triplet molecules. Another way in which you can do pretty much the same measurement is shown here, where you show the whole spectrum as a function of time. Before you start with your pulse excitation, you have an ordinary absorption spectrum that's shown here. You excite at this wavelength and continue to measure the spectrum. Well, now you have a negative peak here and a positive peak there. The positive peak measures the disappearance of the ground state, which these are difference spectra. And the negative peak is due to the triplet absorption. If you measure the triplet absorption independent in solution, you get this dashed line. You see the peak is shifted from the solution to the solid a little bit, not a whole lot. So this is a fairly characteristic triplet absorption of diphenylizobenzofurane of furan. And you can evaluate these curves, and from that we got this number 200 plus minus 30%. So yes,
Can I ask a question? Can I ask a question, Professor Michl? Yeah.
Go ahead.
Yeah. So the blue trace is the singlet decay on the left hand plot, right? and the black trace underneath it is the ground state bleach dynamics, right?
Yeah.
So I can see a very nice correlation that as the blue trace goes up and starts decaying out, it has two components. It has a fast component and it has a slow component. Mirroring it is a ground state bleach in black, which is again having a fast component of recovery, but then having a slow component of rise. So do you think that in the initial 1 picosecond or so, you lost some of the excited population back to the ground state because your bleach has a short component of recovery, like a very fast component of recovery, and then a rise again?
Yeah, this is the interpretation is not as simple, because each one of these curves does not measure purely just one component.
Okay.
The black curve is a combination of the ground state bleach and triplet absorption.
Okay.
Because we don't really have a wavelength where we would cleanly just observe one species.
Okay.
So everything is a little more difficult to complicate.
Got it. So you need to do some decomposition, singular value decomposition.
Exactly. You do global analysis.
Global analysis.
Then, yeah, and then you get this curve, which is now the pure bleach.
Thank you. Thank you. Okay.
And there is actually an additional complication. You are right. This is not a mono-exponential process. There is a component that's fast and another component that is slower.
Okay.
Yes. Now, okay, so why is it that you cannot go to a supermarket and buy a solar cell that uses singlet fission material and is much more efficient than an ordinary solar cell? The reason for that is a materials problem. There are now something like maybe 10 or 8 known compounds, structures, that give 200% triplet yield. And you need to get something very close to 200%, because that number I gave you of going from 1/3 to 1/2 or almost to 1/2 only applies if you really make 2 triplets out of every photon. If you're only making 1, you get from 200 to 100%. Well, then you're gaining absolutely nothing. So that would be useless. Already something like 150 is pretty close to useless. You really need to be very close to 200 to make it a practical, useful product. Well, of all these structures here that are known, this is not a huge number. If I were an engineer and somebody came to me and said, build me a singlet fission solar cell, I would ask him for a list of materials from which I can select. And if he only told me tetrasenes, pentasenes, hexasenes, I would probably just laugh at him, because these materials are mostly impractical. They will not survive on the roof for a day. So we need new materials that would be sturdy and have not just the property of making 200% triplets. They would also have to satisfy all kinds of other requirements in order to be practical. And so the best way to proceed is to look for structural design principles that would tell us what materials to synthesize in order to make this practical. Now, there would be several aspects to such design principles. The first one is the design of the chromophore itself. We have to choose chromophores that have this property of a T1 state being located halfway between S0 and S1. Otherwise, the material will give singlet fission that is not approximately isoergic. And so if it is endoergic, it will be slow and other processes will take over. If nothing else takes over, then fluorescence will take over.
Can I ask a question here? Can I ask a question? So there is a question in the chat box by a student Arup Kundu. Arup, could you unmute yourself and ask the question?
Yeah, hello, am I audible?
Yeah. Yes.
Yeah, Professor Michl, I have a question from the last slide. So just a technical question. There you mentioned at 77 Kelvin, you have efficiency of 200 plus minus 30%. So I was wondering that theoretically I can get maximum 200% efficiency. So I am having a distribution of plus minus 30. So what does that mean when 200 plus 30? What do I mean by 215, 220 efficiency? Is there more than 2 triplet generation from one singlet? Or
no, there is not. There is not. This is just the error margin on my measurement.
so then how can I get more than 200% efficiency from an experiment while I am having theoretically maximum 200% efficiency?
Yeah, you cannot. This
Okay.
does not tell you that you can make 230%. It tells you that the error of the measurement is 30%.
Okay.
Okay, and one more question I have, Professor Michl, on this slide. When you arrived to this structure, and now that you are discussing the structure function aspects, when you thought about this structure, was there a careful sense of arriving to it, or you were looking for a favorable singlet triplet gap?
Well, both. I knew what kind of structures are likely to have a favorable singlet triplet gap. Well, it's not only singlet triplet gap, it's both gaps, S0 to T1 and T1 to S1.
Right.
And I will tell you in just a minute what that argument is.
Perfect. Thank you.
So what I stopped was when I was starting to tell you that I don't really want the singlet fission process to be very exoergic either. It might go well and fast, but all that heat that is produced in the reaction, if it's exoergic, is going to be wasted. And that's why hexacenes, for example, would not really be good, because the energy of the two triplets that you're making is quite a bit less than the energy of the S1 state that you're starting with. And the difference is lost as heat. So you want to be pretty close to equality, pretty close to the isoergic limit. Actually, it would be ideal to be slightly endoergic, but we don't need to talk about that. Now, this represents a very large search space, because in principle, you could look for a compound that has roughly 1.1 electron volt triplet energy and roughly 2.2 electron volt singlet excitation energy among millions of compounds. And how do you find the group that is likely to meet your requirement? The second point to consider is that after you have identified a good chromophore, which has the levels where you want them, then you have to decide how to organize the chromophores in the solid, in the crystal, because it may matter whether the molecules are parallel to each other or perpendicular or close to each other this way or that way. There are 6 degrees of freedom in deciding how to arrange 2 molecules, and of course many more degrees of freedom if you have many molecules. So you need some sort of principle or design idea that will tell you how to do well. And this is where we come to that Fermi golden rule that we are using in the approximate analysis of the situation, which tells you that the rate of singlet fission will contain the Planck constant here, and then the square of an electronic matrix element from going from reactants to products, and multiplied by the Frank Condon weighted density of states. That's this row of E S1, S0. And you need to optimize these factors, make them large, in order to get a large rate. And that's a consideration that we'll return to. But not only do you need to make the singlet fission rate fast, you also want to make the rates of all competing processes slow, because it won't help you if the singlet fission occurs in 1 picosecond instead of 25, if something else, maybe excimer formation or photochemical reaction or some other process, occurs in half a picosecond. So that's, both of these considerations are important, because it's not the rate that matters, it's the yield that matters. And that depends not only on the rate of singlet fission, but also on the sum of the rates of all processes that depopulate that excited state S1. Now the search space, even for just 2 molecules, would have 6 degrees of freedom, because you can take the center of mass of each molecule and displace it from the other by x in the x direction, by y in the y direction, by z in the z direction, and then you can rotate one of the molecules around the x-axis or the y-axis or the z-axis. So this is not an easy search. You're searching for a minimum or a maximum, depending on which of these two you are looking at, in a 6-dimensional space. And then, of course, you have another consideration, which is, what do you do about the structure of the solid that would allow the charge separation and collection to occur well? That means that your excited triplet or singlet has to travel through the solid fairly easily, some distance that is sufficient to bring it to an interface where it then splits into a positive and a negative charge, the way that we saw in the diagram that I showed in the beginning for n-doped and p-doped silicon. So this is a tall order. This is a large number of things to think about. And I have here a list of the sort of standard requirements that need to be met by any compound that you want to be practical. Sure, you have to have a 200% triplet yield or close to 200. That means you cannot afford any competing photochemistry or photophysics. You want the T1 to be about 1 electron volt excitation energy. T2 and S1 should be a little above 2 electron volts. The reason I want T2 to be above S1 is that I don't want annihilation of T1 plus T1 to give me a T2. If the T2 is too low, that annihilation will become possible. I want the T1 to be long-lived, so it can make it to that interface where charges separate. And I don't want any triplet-triplet annihilation or recombination. If I have charges traveling through my solid also, and in some of the possible designs they would do that, I don't want them to quench my triplets. Radical cations and radical anions, or polarons in the physicist's language, have an ability to quench triplets. I want to avoid that. Redox potentials of material at the phase have to be matched. So the charge separation actually occurs efficiently. I want charge separation from T1, but I don't want any separation of charges from S1. I want the S1 to undergo singlet fission and not to separate charges. Then there are more technical problems, like I want good interface adhesion. I may want a particular morphe. I definitely want a high extinction coefficient throughout the visible, because otherwise my layer will have to be too thick to make sure all photons get absorbed. And if I want my excitons to travel through a thick layer, they are probably going to get lost. And so that's not good. The layer should be thin. The extinction coefficient should be high. You want a material that's light fast, it doesn't bleed in sunlight, and sturdy. It doesn't get oxidized. You want a material that's cheap, and ultimately you want a material that's non-toxic. That's one of the arguments against the use of lead-based perovskites, for example. Ultimately, you'll be getting rid of old solar cell panels, and you don't want to be spreading lead through the environment. And this is probably not a complete list. These are just things that I thought of. So,
sorry, this is just a naive question. You said somewhere on the slide, it says avoid triplet quenching by radical ions. Is it this? What is the source of these polarons in a device?
Well, depending on how you design the system, you may have to ask the polarons, the radical cations, say, or anions, to travel through your layer to the other electrode.
Mm-hmm. Okay.
You have some interface where the charges separate. T1 gives you a radical cation and a radical anion, and one of them has to go to one electrode, and the other has to go to the other electrode. And in certain designs, that requires it to travel through the active layer. And it may be unavoidable in such designs. And in that case, you want to have a low enough concentration of these holes that they don't quench your triplets.
Okay, fine. Thank you.
All right, now we come to this point number one that was here. How do we design the chromophore? So the question is, how do we make the gap between the ground state and the triplet excited state just as big as the gap between the triplet excited state and the lowest singlet excited state? And what we thought of back in 2006 was that a group or class of materials that's likely to satisfy that requirement would be biradicaloids. For that, I have to explain what I mean by biradicaloid. I mean, I think people generally know what a biradical is. That would be a species that typically by symmetry has two singly occupied orbitals. Instead of having a closed shell in the ground state, it would have an open shell character. A biradicaloid, and that's from Greek, right? The ending oid means similar to or like. So colla is glue, and colloid is something that's like a glue. So that would be a molecule which is sort of almost like a biradical, but not quite. So it's between an ordinary molecule with a closed shell ground state and a biradical. Let me illustrate that by examples. The simplest biradical is a pair of hydrogen atoms. If you think of the potential energy curves for the H2 molecule, as you have them shown here as a function of distance between the two protons, and here is the energy plotted vertically. The ground state, that's just the Morse curve for the H2 molecule. You have the bound molecule here, and to dissociate it, you have to go up in energy, and then ultimately you end up with two hydrogen atoms which hardly know about each other because they are so far apart, and this goes on all the way to infinity. That's the ground state. The lowest excited state is a triplet. That would be also H plus H plus. So H dot plus H dot. But now the two electrons would have the same spin. Instead of being one alpha and one beta coupled into a singlet state, they would be coupled into a triplet state. If you try to push such two hydrogen atoms together in the triplet state, they will not make a bond. You cannot put both of those electrons, if they are both alpha, say, into the same bonding orbital. One has to be in the anti-bonding orbital. And so the energy goes up. And the curve looks as shown here. It just keeps going up and up. So in this situation, on the right-hand side, you have a nice pure biradical. It has two orbitals at the same energy, and both are singly occupied. By the time you get to this geometry, it is an ordinary molecule. It's not a biradical at all. In the ground state, it has one bonding orbital occupied twice, and in the excited state, it has one electron in the bonding and one in the anti-bonding sigma orbital. How about the excited singlet state? Well, to make an excited singlet state out of this biradical, H dot plus H dot, you have to move one of the electrons from one hydrogen atom to the other. So you end up with H plus, H minus. That, of course, is much higher in energy than H dot, H dot. And so you have a large excitation energy to the S1 state. As you need two ions closer together, the energy goes down because plus and minus ions attract. And you end up with this minimum, which is at about twice the bond length in the ground state. In the ground state, it's about 3/4 of an angstrom. And in the excited singlet state, the minimum is at about 1.3 or so, 1.35 angstrom. So you can see that in the biradical limit, you are not meeting the requirement that I have here. I don't have the excitation energy to the singlet approximately twice the excitation energy of the triplet. This one is big, that one is big, and this one is 0. So that's no good. If I go to an ordinary molecule, I have the usual situation in which the excitation to the lowest triplet takes almost as much energy as the excitation to the lowest singlet. So again, I'm not meeting this condition. But these lines, these curves are continuous. And that means that I have to have somewhere a situation in which this distance is the same as that distance. So it's in between. It's not where I have an ordinary molecule, and it's not where I have a pure biradical. It's somewhere in between. And you can see here the blue and the red arrows, they have the same length, and they are indeed located somewhere in between. That's a biradicaloid geometry. Here's another example, ethylene. You can twist ethylene, and in the ground state, it wants to be planar. You can twist it about 180 degrees, and you get back to where you were. So these energies are the same. But when you are at 90 degrees, you have a biradical, because the two p orbitals are now orthogonal to each other. They cannot make a bond. Electrons in them cannot make a bond. And so in the ground state, each one will contain one of these electrons, but the energy will be something like 65 or 70 kilocalories per mole higher than it was, and the molecule was planar. In the triplet state, the opposite is true. When the molecule is planar, the molecule is less stable, it has higher energy than if the molecule is twisted. The excited states are complicated in the case of ethylene, but roughly speaking, the situation is as shown here. Actually, these are quite good calculations, although they are taken from this book on organic photochemistry, which is dated, but already back 30 years ago, you could calculate ethylene quite well. In this example, you see that you actually could start with a biradical, and that would be again terrible, as it was terrible here, because you would have essentially zero excitation energy to go from A0 to T1, and you'd have a large excitation energy to go to S1. And this time you have to go away from the pure biradical, and you have to go pretty much all the way to a planar molecule to get where you want to be, where these two are the same distance. So now we get to the way in which we deduced that diphenylisobenzofurane would probably be a good molecule to look at. It would probably have the right energy levels for the singlets and the triplets. That's because if you think of benzene and you attach two CH2 groups to it and you twist them 90 degrees such that they are not conjugated with the pi system of benzene, then you have something that's pretty close to a perfect biradical. That would not be good. I need to go toward an ordinary molecule. I can do that by twisting these two CH2 groups such that now they are in conjugation with the pi electron system. Now I have a biradicaloid. And to make it stable, this molecule itself is known. We studied it actually back in the 70s. And it's extremely reactive. So this would not be useful. But you can tie these ends with an oxygen atom. And then for additional stability, you can put a phenyl substituent here and also here. And then you end up with a molecule that you can actually purchase. This is commercially available from Aldrich. But it still has this property of being a biradicaloid. It's not quite an ordinary molecule. It's halfway towards something that would be a biradical. And that was the argument that we used to choose this molecule. That was actually the first molecule that was sort of intentionally designed to be good for singlet fission. But there was a good piece of luck in using this molecule and finding that it actually gives, with an experimental error, 200% triplet. And the luck was that it packed correctly. We had no idea how it would pack in the solid, but it just happens to pack correctly. You might also want to ask the question, let's see, how much time do we still have? Well, we had some...
we are close to pretty much 1.5 hours now. So maybe we can take this up, the captative substitution, maybe in the next talk. Is that okay with you? Or
yes, this would be a logical place to stop. Yes.
Yeah, and we can take some questions here at this point.
Okay.
Yeah.
Okay.
Satish, is that okay? Satish?
Yeah, it's fine. Please.
We can have this maybe the start of the next talk and take more questions. There were 2 questions that one of the panelists, Ravi Kishore, Professor Ravi Kishore, could you please unmute yourself and ask the questions on concentrations and also the triplet annihilation? Ravi Kishore, are you here? Ravi? Okay, I'll just ask what he had mentioned in the chat. He had asked that for singlet fission to occur, the concentrations in solution must be high. What are the typical concentrations in solutions that we use?
The singlet fission is usually not done in solution.
Okay.
In a solar panel, it would be a disadvantage to have solution. You have to remember that it has to stay on the roof through hot and cold weather for many years, hopefully. It will leak, it will be nasty. So engineers generally try to avoid having to have a solution.
I think
there's no great advantage to it.
Right.
You can study it, and then if you study it, you typically use a saturated solution, as much concentration as you can get.
Right. This for the experiments, I guess he was mentioning for the transient experiments. They were done in films, I guess, right? You did it in films.
Yes, there were a few that were done in solutions and maybe on 2 or 3 different compounds. The rest of them are all in solid films.
Okay.
Or in single crystals. You can study this in single crystals.
Right. And the other question he had was, is there an equilibrium between singlet fission and TT annihilation?
Yes, there can be. For some molecules, it has been studied. It depends on how the levels are positioned relative to each other. But in tetrazine, for example, that's a very nice example. It's a slightly endothermic singlet fission. And there people have looked in great detail at processes going from the left to the right and from the right to the left. Yes.
Right. Okay, now I'll invite all the panelists to ask questions.
Okay. I can maybe, JD, can I start?
Yes, please.
So this is one of the critical step you mentioned about diffusion of triplet to the interface. And I simply wonder, because this is a neutral triplet exciton, it does simply diffuse by the process of a concentration gradient, or is there any other driving force for it? Because that is something which is very critical. Until unless the triplet, it reaches to the interface, the dissociation would not happen. So this
That is correct.
this
Yes.
diffusion of a
And
triplet,
the triplet excitation is localized typically, maybe always, on just one molecule, and it jumps from one molecule to a neighbor that's touching it by the Dexter mechanism, basically. And because the triplet is generally long-lived, hundreds of microseconds would be typical, it can cover quite some distance. It has an advantage over singlets that way. But of course, it does not guarantee that it will make it to the surface. It is not driven. It's, as you pointed out, there is a concentration gradient, but typically it's just a random walk that the triplet is making. And the disadvantage that it has is that it's relatively easily quenched. If there is oxygen, for example, molecular oxygen in the solid, that will reliably quench triplets. So you don't want that. And usually that's not a big problem because these are solid, dense crystals and oxygen does not diffuse through them too well. But it is definitely true that trapping is a big enemy.
Sure. Thank you.
Okay. We have two quick questions. I think 3 questions now. Well, we'll start with Vivek. Professor Vivek Tiwari, could you unmute yourself and ask the question?
Thank you, Professor Michl, for the tutorial style talk. I just had a quick question about when you said the packing of these molecules in films was a matter of luck. I had a related question that, so there are proposals, this is about singlet annihilation where, when molecules pack as J versus H aggregates, the annihilation rates could be different. So my question was, so my thinking is that those considerations might also be applicable for triplet annihilation. And then the question was whether these considerations also go into play when we think about, how are these molecules really packing in the film.
Great.
Yeah, so the triplet annihilation is not such a big problem because it slows down the eventual formation of the 2 free triplets that you want, but it does not in itself waste energy, because if you recombine to make S1 again, well, then you are where you started and singlet fission can again take place. So you have wasted time and increased the chances that something else will compete successfully, but it is not a complete loss. Whereas other mechanisms that compete with singlet fission are more likely to be a complete loss. If, for example, you have inner system crossing, and then you get 1 triplet out of 1 singlet, and plus a lot of heat, that does not go back. And so you have just lost your chance to make two excitation carriers. If you make an excimer and the excimer is only weakly bound, it can go back. But if you make an excimer that is strongly bound, it will not be able to go back. And again, you have wasted your excitation. If you make a charge separated state, radical cation, radical anion combination, and if that is sufficiently more stable than the S1 state was, once again, you have wasted your excitation. So typically, these are the biggest problems, not so much the triplet annihilation.
Okay, thanks.
Okay. Okay, I'll like Professor Ayan Datta to ask his question.
Yeah, Professor Michl, I mean, this is a small clarification. I mean, how much in terms of the, for example, when typically we are considering, I mean, two molecules together, and when we have two molecules together and their internal electron transfer dynamics, how I mean, in terms of the kind of precision, I mean, how good as an approximation is the electronic energy changes with respect to the free energy? Because I'm not able to, because as you understand at a quantum level, it is very difficult to quantify entropy. So, I mean, in terms of the precision and if at all the approximation, I mean, how good an approximation is the electronic excitation energies of the states with respect to the free energies, the so-called free energies?
Yes. In general, the free energy favors singlet fission because there are more ways in which you can generate these biexciton pairs, molecular pairs, than you had in your initial singlet excitation. But I must admit that most of the time, people who study singlet fission do not bother with the evaluation of making the difference between free energy and potential energy. And so there is an area where some additional research would be very useful.
Okay. Okay. Is that okay, Ayan? Okay.
Thank you.
Okay. Okay. I will like to ask now Professor Devashri Ghosh to ask her question. Devashri, could you unmute yourself?
Yeah, sure. Hi. So I have a strange question, I think. Basically, you were talking about this triplet diffusion in the last process where, you know, the triplet pair kind of becomes unpaired and goes away, and that's how you see the final effect. So can it somehow be driven? What I mean to say is, why do we always think about the same molecules doing the singlet fission rather than having small changes to, you know, like a sort of heteromolecular separation and therefore some kind of a charge-driven, you know, driving process? Did my question make sense?
Yes, it makes perfect sense. You can, so first of all, the singlet fission that involves two different molecules that have different triplet energies has been observed. That's a known phenomenon.
Okay.
And you can see that in doped crystals, for example, in doped single crystals. But the moment you introduce this, you are wasting energy. You're losing energy. So you have if you had a structure which is sort of built in such a way that this will provide a gradient that will drive the triplets in the direction where you want them to go, you are getting an advantage, but you're paying a price. You're losing some of the efficiency. You're wasting energy.
I see.
Yeah. Mm-hmm.
And it's never going to favor this, I mean, because the driving is in some way, whatever I'm getting as triplet, I'm getting back as a, you know, effective triplet. So that is never going to be more beneficial than the energy loss that you're talking about. Is that how I should interpret it?
that is probably true. I think that any time when you go from a higher energy triplet to a lower energy triplet, converting difference into heat that you're not going to get back. That's going to be wasted energy.
Okay,
And
thank you.
There could be circumstances where this might be worth the trouble, but I don't think anybody has ever figured out how to take advantage of them. I can give you an example of a situation where it might be perhaps useful. One of the ways to separate charges is to deposit the organic layer on top of silicon, just an ordinary silicon solar cell. Then, if the triplet reaches the interface between the organic phase and that silicon, it might, in one of several possible mechanisms, transfer the excitation energy into the silicon. And in silicon, the exciton will immediately dissociate into free carriers, and you will have what you wanted. So in order to promote this, you might want to functionalize the silicon surface with a thin layer of some molecules that will sort of grab the triplets and transmit them farther down to the silicon at the cost of losing some excitation energy, because the triplets that you attach to the surface this way would have to be somewhat lower in energy than those that are in the bulk solid, organic solid above them. So there is that loss. Whether you could, under these circumstances, gain enough from a rapid transfer of your triplets into the silicon, I don't know. I don't think this has been looked at.
Right.
I see. Okay, thank you.
Okay. Now there's a question by Professor Ravindra Venkatramani from TIFR. Ravi, could you unmute yourself and ask the question, or maybe video also? Possible.
Hear me?
Yeah. Yes, Ravi. Ravi, we lost you, I think. Ravi?
Yeah, can you hear me?
Yes, yes.
Yeah. Materials which actually where you got 200% yield, right? So whether was the yield free triplets or was it still bound triplets?
That's a very good question. Frequently, people do not know whether they are looking at biexcitons or really free triplets. And sometimes, in some cases, there were reports of very high triplet yields, which then later, some years later, turned out to be only biexcitons, and the triplets were never free. It is when you do only optical observations in the visible or near IR, or maybe even UV, but usually not, it is very difficult to tell them apart. They look spectrally the same.
I see.
So yeah, you may be pointing out that the number of materials that really produce free triplets, useful triplets, is even smaller than the number that has been claimed. That could well be.
Yeah, so I was wondering, yeah, so along those lines, I was wondering for the generation of free triplets, which would be the ultimate goal, should you think of it as a purely electronic problem, or do you think that the material should undergo some kind of a phase transition to actually really separate these triplets out, actually, right, in terms of engineering such materials?
Well, I think that there's typically some binding energy, and that it would be of electronic origin. If you think of the two triplets independently, separated by some distance, then compare that energy with the triplets right next to each other, there can be configurations that you can write down for the interacting triplets, like charge transfer configurations, which are absent or very high in energy once the triplets are separated. And so you have to break this resistance. So there is a price to pay, maybe not a very large price, but there is a price to pay to separate the two triplets. And the density with which these charged species or excited species occur in the sample, whether it's in the laboratory conditions or if it is in sunlight on the roof, those densities are very small. So you would have a large distance from one triplet to the next. And I don't think that that would induce a phase change in the material.
I see. Okay,
Now,
thanks.
there
And
is
then, yeah, if I can just add, just for my information, just a question. You mentioned that singlet fission was observed in crystals. Is that right? So is it
Yes.
possible?
Yes, yes. Actually,
So that-
singlet crystals provide a lot of useful information compared with these polycrystalline monolayers or layers.
Right. Okay. Thanks a lot. Right.
Yeah, okay. I have a question from Arup. Arup, could you unmute yourself?
Hello, am I audible?
Yeah.
Hello.
Yes.
Yeah.
Yes.
So I have a question for Professor Michl. So as we are discussing about these optical signatures of these biexcitonic states versus free triplets, just extending with Ravi's question. So if I am depending on the strength of the coupling between those two chromophores, for considering the dimeric model, so do we expect large spectral difference of this biexcitonic state versus free triplets if I am a strong coupling regime, or they should be more or less similar? Either of the cases, and of this, if I consider the spectral signature of this biexcitonic state versus the free independent triplets.
Given the typical width of the peaks of the band, absorption band, observed in the spectra, the similarity is quite striking. There is just not much difference. If we could get a much more highly resolved spectra, you would probably see the differences quite clearly. But we're talking about peaks that often have 50 nanometers, 100 nanometers, maybe even more bandwidth, and there's no fine structure in it. It's very difficult to tell whether you have the free triplet or the biexciton.
Okay.
Yeah. My question is slightly different. Do we always expect that it should be similar in spectral signature, or there might be some cases where, depending on my coupling strength, I can get different signature, and that should not be surprising if I get some distinct different signature?
I cannot remember any case in which this was observed, where the spectra were, well, maybe there is one or two cases.
Yeah, because I can remember there was a one
different,
yeah.
Tell that they are different.
Okay.
Yeah.
Okay.
I just wanted to add that in that part that if you were to resolve it from the 1D to the 2D spectroscopy, to the electronic spectroscopy, that might help in resolving biexonic states from a purely free triplet. But then you have to resolve it into two different dimensions along the electronic spectra. The other aspect to it, I think, is Professor Michl, I think you're right. There is no way. It's very hard to have these spectral differences, but there are a few reports, and in fact, some of the work that we have been doing now, carotenoids do seem to show a promise of separating out TT versus T. So that's something that will come out soon. But I think I really kind of am interested in sort of asking this, the range of the coupling strengths that one can engineer in these systems, the coupling between the triplet pair states. Do you envision a way to systematically modulate it?
Well, we have done some approximate calculations of these binding strengths. I presume that's what you're referring to.
Yes.
Okay. So the binding energies that we calculate are typically measured in tens of millielectron volts.
Yes, very small, right?
Yeah, very small.
Yeah. And
But in principle, of course, you could think of ways of doing this, and I'm sure people are thinking, because it's an important consideration.
yes.
You could take a look at the temperature dependence,
Yes.
so on. But that's a pretty unexplored area.
You're right. And the other part is the vibrational spectroscopy of such states, correct?
Now you're talking. Yes, if you could measure in the mid IR instead of the near IR, or even worse, visible, you could go much farther. Yes.
Right. Yeah, that's something that would be through IR or Raman measurements. It would be nice to follow. Okay. Are there any more questions from students? I would like this is very rare we get a chance to talk to an expert, a leader in the community. So are there any questions from the students? I'll give 10 seconds. Any more questions from students? All students are panelists this time. This early hour, I was not sure how many people would join, but we had 35 people joining. So,
okay.
Yeah, but this is all on YouTube now, so people can revisit the entire lecture. Any other question from any other panelist? Okay. Well, if there are none, Professor Michl, can we have your video on, please? Maybe we can stop the share and have your video.
Let me see what I can do here.
Yes, sure. I presume it's 8:30, close to 9 o'clock in your time zone.
Yeah, 5 to 9.
5 to 9, yeah. That's Professor Ravindra Venkatramani. Hi, Ravi. That's Professor Ayandatta. So they're all putting their videos on. So yeah, I would really like to thank on behalf of everyone joining here, Devashri, this Professor Devashri Ghosh. So I would like to thank you for taking this time for the first lecture and really working through some technical glitches, but patiently explaining us the concept, the starting part of the concept of singlet fission, and also mentioning important considerations for the solar energy technologies. So thank you, Professor Michl. We look forward to your second talk tomorrow exactly at the same time, and I will again join at 30 minutes before that so that you are comfortable. Okay.
Excellent.
Thank you very much. Can we have a big round of applause? Can we have a big round of applause, because we can't get this in physical. The warmth is not shared physically. So thanks.
Thank you very much for your kind attention.
Yeah, thank you. Okay.
See you tomorrow.
Yeah, see you. I'll close this session now. Thank you, guys. Thank you for coming.